So let us start with the topic of simple harmonic motion. About SHM, we can write that the definition first. As usual, we have studied circular motion. Now it's time for us to study oscillatory motion, which is a very good example is the SHM. So about SHM, let's write definition. We say SHM is a periodic motion of a body. So I will just write SHM, which is simple harmonic motion, is a periodic motion of a body in which acceleration is directed towards a fixed point. And it is proportional, and it is proportional to the displacement from that point. Now, from this definition, what we are trying to say is that it's a special type of motion. What we call SHM in physics is just a special type of motion in which you have the acceleration of the body is directed towards a fixed point. From what we have studied, it is a type of motion. Like, look at this. If we have a good example for what I'm trying to say, I hope you can see what I'm trying to bring out. You have a line. Here we also have it's a periodic motion. That is it goes what people call it in early classes to and fro about its mean position. So this is a body. It's having its mean position at a general time of let's say this is the mean position at x equals to 0. So particle is moving to the maximum position here we call plus a, and is amplitude positive, or at another time it comes to this position we call what negative a. So these points at which the motion is starting is called the mean position, which you might have studied in early classes. Mean position, whereby the other two positions at the end of this circulation is called the extreme positions. So now, or you say maximum position, anyhow you want to call it. So now, extreme position. So now, when a particle moves from its mean position to an extreme position, let's say this particle x is now moving from this point and cover a distance from this point to a general point, and it has gained a particular acceleration of or let's say it in this way, we said as the body moves from one point to another, undulating, say to and fro motion, the acceleration of the body is now what equals to the displacement. So let's say the body here has now this particular body at this mean position has accelerated and moved from this place to a particular point here, and it has gained an acceleration of plus a. So what we say as a simple harmonic motion is when we say the direction of the acceleration a is proportional to the displacement. Displacement can be negative or positive, because if it is moving towards this side, it is positive, and if it is moving towards this side, it is negative. So if acceleration of that body is proportional to the displacement of that body, I will write as negative x for now. Such condition, we say that particular body is exhibiting SHM. So the two things that you have to always put in your definition for those that are defining SHM is such a body in which first thing is acceleration of that body is directed towards a fixed point. So when it goes to the fixed point, what happens? It comes back to here and can also go back to the other side. So that is why you said is a very good example of a very good example is a simple pendulum, which we've talked about in our circular motion aspect. So keep that in mind. First thing is acceleration is directed towards a fixed point. Then acceleration must be proportional to the displacement. The displacement I'm taking at s. So the acceleration of the body starts moving to gain some kinetic energy, which to accelerate, which will make it gain some kinetic energy, which you know. So we are still going to discuss about this as we move on in the topics. So we can bring some conditions which I believe is needed for SHM. For body to undergo SHM, the following conditions must be met. The first conditions you can keep at the back of your mind is for SHM to occur, we say one is the acceleration of the body. Number one, acceleration of the body, just say, must be proportional to the displacement. Very important. No matter how you have it, if you have a general equation, let's take one example. Look at what I'm trying to say. A body is moving in positive x direction, then the direction of the acceleration must always move with respect to the direction of the body. So, and when it reaches a fixed position, it will come back so that you're able to come back towards its original position. So that is what we talk about conditions. Then the second condition, I'll be writing it mathematically. So we say amplitude, the amplitude of oscillation must be small. So this is another important point you can always keep at the back of your mind when you are talking about SHM. So the amplitude of, and what is amplitude? We say the distance between the main position, that is the initial position, and the extreme position. Main position is also the starting point. So distance from here to here is what I call plus A. That is distance covered from this point to this point. That is plus amplitude from here to here is negative amplitude. I have 55 minutes for this video. That is why I have to rush out, and then I have to rush. I'm giving 55 minutes and I have a lot to talk about. So be that as it may, the amplitude of oscillation must be small. Is one of another characteristics that's what even the most important characteristics for SHM to hold. For example, if a body is having a body is exhibiting SHM and it's given as an equation as the body is having an equation of let's say y is equals to c1x, or let's say the acceleration of the body, let me take it as a plus c2x squared. You can see now y equals to c1x plus c2x squared. Now, for example, if you can see, this is a kind of quadratic equation because the power is what is raised to power 2. But what we are saying now is that if the value of the amplitude, that is the x stands for the distance in which it is covering at a point in time from the beginning. So if the value of x is if the value of a is very, very small, as a is proportional to x, I mean amplitude is proportional to the displacement. So we can say x squared is very, very small too, and we can neglect it to be equals to 0. So when x squared is equals to 0, we can say directly that now then acceleration will be proportional to the displacement. So what we are trying to say now is that for every value of measurement, even if it is a sinusoidal graph, I mean sine graph, sine theta 2, if the value of the amplitude is very, very low, you are always going to have a situation whereby this particular force thing will always hold. So keep it at the back of your mind that for somebody or for a particle or system of particles to exhibit simple harmonic motion, such body or particles in motion must have acceleration which is proportional to the displacement and must have an amplitude that is very, very small. Another important one you can write is not that common, but which is also not part of the syllabus, but you can never say, is that the body must exhibit what must be in a straight line. So it must be straight line. Body must be in a straight line. So you can just put down a note because I told you I'm rushing. Sorry for that, my dear students. I have to cover a lot of things under this topic. So straight line motion. So if the body is exhibiting straight line, it is very easy for that body to go in simple harmonic motion, but not necessarily because it's not one of the most important points, but it is also very, very well important in some examination. That is why we are also going to talk about that as one of its conditions. So guys, about simple harmonic motion definition, acceleration must be directed towards a fixed point. Acceleration must always be proportional to the displacement. I never tell you square of displacement, but to the displacement, which is one of the most important factors in understanding this. So let's move to the next slide. Like I said, we don't have much to talk about. We'll move to the next slide. Fine. Now, representation of simple harmonic motion. Now, from what we have studied on circular motion, we've talked about body undergoing circular motion and moving with constant speed if it is uniform circular motion, and the speed or constant velocity. You understand? I'm talking about, I said constant velocity or constant angular velocity if it is uniform circular motion. What we notice in simple harmonic motion is also that we can represent simple harmonic motion in the form of what? Uniform circular motion. Now, what am I trying to talk about, my dear students? What I'm trying to talk about is that we can just write a general note that the projection, you can just write this, the projection for understanding sake, the projection of SHM, of a body in SHM, so that we write well, of a body in SHM can be represented by emotion, by using or can be represented by uniform circular motion. Which we have talked about, if you still remember, under which I call UCM, uniform circular motion. So what are we trying to say, my dear students? Now, if we have a body, I'm trying to show an illustration for understanding's sake. That is a body which is in uniform circular motion as discussed. So if the body is in UCM, the body is here. Just want to show an illustration for understanding's sake. Now, from what we have talked about, this is the body. Now, if it is starting at a particular point, which is what the mean position, initial position, the starting point, as what we have talked about in the previous slide. This is the body starting from here. Excuse me. The body is starting from this particular point. That is the point of starting point. Then it is now moving with what we say at this point, it is general time is time t is equals to 0. Okay. This is the way we've been talking about this time and time again. So the body is starting from time t is equals to 0. Then what we see is that what it is now moving up with angular speed. You know, in uniform circular motion, angular velocity is same. So of omega at a particular time. So the body reaches here. I hope students are getting that. It is starting from here, which is here. Now reaches here. We can draw a line to show that the body is now here. From what we have studied before, as you can see. So what we are trying to say is that the body now started from rest. This is the initial point. At this initial point, it gets to its maximum point at this point. Then what happened? It will fall back. I getting it now? It will fall back to this point. Then it will go back to this point again. And it will go back here. You can see that is undulation. The body is undulating. Excuse me. When the body is undulating, we say such body is undergoing simple harmonic motion. In junior classes, you have a lot of examples. A very good example is the simple motion of what? A simple pendulum, a pendulum bob, which we have also discussed under the topic of circular motion. So my point is, look at this. You know, we say if the body is starting from rest, which is what initial position, then it moves here. It will continue moving. Then again, it comes back to its initial position. So the same thing is happening here. In the y-axis here, the body can actually go up and down. So because it can go up at this point now, it moves up, it moves down. So such body from here to here, going to and fro, is said to be what? Undergoing what? SHM. So we say we can use a uniform circular motion to represent the motion of a projection of a body in SHM. So this type of relationship is what we call uniform circular motion representation of what? Of SHM. Then, you know, in physics, one thing that physicists love is that whenever we express anything in terms of another thing, we are generally going to bring out an equation, which is very, very important. Now, as you can see, my dear student, the body is starting from this point, moves up to this point. Let's say at time t is equals to t as usual, starting from t equals to 0 to t equals to t. Then here we say it has moved at what? Look at this now. It has moved at an angle, as you can see here, of what? Starting with what? Moving with constant angular velocity of omega because it's uniform circular motion, covering a time t. So distance from here to here is just the arc, which is what? Omega t. What do I know, my dear students? Distance from here to here is what? The radius of the circle. So directly we can say here to here, we call it radius. And you and I know very well that alternate angle are always going to be equal. So anyhow you want to do it, is always going to be the same. So my point here is that this is omega t, this is your y. So if you want to bring out your half for you to see it very well, then you can go like that and go by your SOHCAHTOA. So this is omega t, and this is what? This is not omega t. You can just try as much as possible to balance this for you to see it. I know my students love seeing everything, so I just want you to see. Don't sleep on bike. It's not good to sleep on bike now. Watch. And if you don't like that, you can do. I'm trying to just balance for you to see. If this is omega t, you know this is also omega t. What do you call the angle? Alternate angles are equal. So this is omega t if you want to go by this side. So from your representation now, we said distance from here to here is what the radius r. So the general equation will be in terms of, because it is moving to and fro at this point when the body is what? Moving at constant speed. So we can see from there, look at this, guys. What's this? Opposite over hypotenuse. What is opposite over hypotenuse? That's sine. So you can say y is now equals to, so the radius is r sine of omega t. So as you can see, this is the way we represent simple harmonic motion in uniform circular motion. So, and we've also studied if we differentiate y with respect to t, y as a function of time, we know we are going to get another important thing we call the velocity. What is velocity? It's distance by time. The distance is the y by the t. So if we do that, we know from early classes, I told you, you watch the videos on the page in sequence. You need to understand differential equations or generally what called differential calculus and integration before you can now come into this. So directly here, you can say the y by dt will now be equals to, the y by dt is velocity, which is equals to, we have r omega cos over omega t. R omega cos of omega t. Then the next one is another property you can bring out is what? Acceleration. So acceleration, from what we have studied, acceleration is also rate of change of velocity, that is the v by dt. So if we go by that, we have it will now be the v by dt, which is acceleration, will now be equals to, let's take this with respect to this, is r omega square. You can see it to be minus, because when you differentiate, what is minus? R omega square sine omega t. So if I substitute from equation 1, I hope students are following. If I substitute y is equals to, look at this, r sine omega t. R sine omega t is equals to what? Y. So I'm going to have a equals to negative omega square y, which is another important formula you can keep in mind, that for acceleration of what. And if you can see that, my dear student, you can conclude from what I said, for a particle to exhibit SHM, what happened? The acceleration must be proportional to what? To the displacement, which is also valid from what we have gotten from our general representation of SHM. So my point here is that the negative sign is just telling us the direction in which the body is moving, either towards the negative axis or the positive axis. So the point here we just need to keep in mind, always, as usual, you always have something to keep in mind, is that, excuse me, is that I think we can go for a white. The first thing you have to keep in mind here is in that the definition of uniform circular motion, there are some parameters we use. Then when it comes to simple harmonic motion, we have also some other parameters we use. So I'm giving 55 minutes for one simple harmonic motion. I am not going to waste time. I'm going to stick to that 55 minutes. So basically, understanding what we've talked about is very, very important. And be that as it may, we can quickly look into what I talk about. Now, under simple harmonic motion, we say the distance from the mean position to the extreme position. You know, under circular motion, we call it as what? The radius. But in simple harmonic motion, we don't call it radius. It is called what? Amplitude. So these are general terms you can keep in mind. Amplitude is A. So in what? In circular motion, amplitude is called what? The radius. So keep that at the back of your mind. Now, another important point you can keep in mind is now when we talk about simple harmonic motion, we talk about angular velocity. You can see angular velocity. Now, angular velocity, which is omega, which is noted by omega. In simple harmonic motion, we don't call it angular velocity. We call it angular frequency. Please keep that at the back of your mind. Angular frequency is angular velocity, because all these are going to be needed as we move on. Then the last thing is another important stuff you can always keep in mind is what we call angular displacement in circular motion. Angular displacement in circular motion. So please, angular displacement, which we call theta, theta here, which is omega t, we don't call it angular displacement here, we call it the face of what? The face of a simple harmonic motion, excuse me. So be careful about this, because direct question in objective can ask you about which of these is the direct equivalence of circular motion to simple harmonic motion. I have seen questions like that before, and that is why I always love to focus on what I've come across before in one way or the other. So this is the way we represent simple harmonic motion, and the representation is always given in terms of, keep it in mind, acceleration must always be proportional to the displacement before you can conclude that it is what? An SHM. So guys, we move to the next slide. No time to waste time. I hope I'm still within time rate. They are not ready to give me a red card now. So the next one, guys, is a general equation of simple harmonic motion, as we have studied. Now, as we have studied in the previous slide, that equation of simple harmonic motion can be represented using uniform circular motion. So as discussed, it can be represented in uniform circular motion when it's starting from a particular mean position. Now, the only alteration or differences in what I want to talk about now is that it is not necessary. It is not necessary for, can you hear me? Okay. It is not necessary for simple harmonic motion, or a body that is what? That is undergoing simple harmonic motion, to start from what? The initial position. That is what we are saying. So when we have situations like that, we can take an example from uniform circular motion that I've explained in the previous slide, but this time around, we are going to talk about the general equation. So here we say, this is this. My circle is supposed to be more big, but you manage it. Circles are now very, very scarce in nature. So from here you have, that is that. Now, if the body is not starting from this point, let's say the body starts from this particular point. I hope students are watching. Now, generally it should start from the mean position. No, what I'm trying to say now is that it is not starting from rest, from the mean position. So the starting point of the oscillation, maybe the body is at the midpoint, or wherever you say it is. Then you now swing it. Do you understand? It's possible now. Jingle over. Jingle over is a good example. Jingle over like a motor. You understand what I mean? So now for this, you have this kind of illustration is telling you that actually the body is starting from here. It's released from there. Then when it starts moving, it will start moving and going through what? Different phases. Let's say it's moved from that particular point to this point. I hope students are following. So at this point in time, we can say the body is not starting from what? The initial position. Watch. Now, this is the motion. What is the difference between what I explained before and now is that it is not always necessary that body is going to start from rest, mean position. Body can start from an extreme, but not even extreme position, a desired position, you call it. So in that case, when you have that, so you say, the body will definitely come back to mean position, as we have talked about. When body swing up, when the body is no more accelerating, what happens? It goes back to what? Its initial position, which is the main position. So be that as it may, my point here is that at this particular point, it's still moving with angular velocity. So let's say initially, the angle between this and this is alpha. We represent this by alpha. I'm just speaking the general terms that you've just seen in your test material. This is alpha. I want to write alpha. I'm writing omega, which is not where the motion is starting. So here, the body starts moving here with angular speed of omega at a time t equals to 0 to t equals to t. This is not always necessary, but it's just for understanding, say, for our advanced students, which they can be asked to prove any formula at any point in time. So now at this point in time, which the body starts moving, it will move with what? We talk about that omega t. So the total angle of oscillation from what we've discussed, we said now we don't use radius. The radius distance from here to where it is here is what? Amplitude. So if you balance that, you can going to say, well, y is now equals to, let's just write, no, our radius now is now a, the one we write before is a sine omega t. But in this case now, if you watch, the total angle of oscillation here is what? This is omega t plus what? Plus alpha. So you now say y is equals to a sine, this time now that is not starting from what? Rest. We say a sine omega t, can see omega t plus what? Plus alpha. This is the equation we call the general equation of SHM when it is not starting from what? From mean position. So now you also need to understand something for those of us that we are mathematically inclined. We should understand that when a body is starting from what? Is the angle between, when the body is starting from mean position, it is making something like a right angle triangle. I hope students are still here. So look at this, guys. This is what I'm talking about. The body is here, and this might changing stuff. We have this and this. We know the angle between this point and this point. Mathematics students, we know where they know better is what? 90 degrees. So what I'm trying to say here is that the total angle here is what? 90 degrees. So what I'm trying to say now is that at initial phase here, the angle is what? 90 degrees. So 90 degrees you write as 90 degrees, you write as pi by 2. I hope you know this. That is, I've converted 90 degrees to radians. I mean, 1 pi is 180 degrees. Mathematics students can tell us better. So if I rewrite this, I can say, so y is equals to a sine over omega t plus, what is alpha now? Pi by 2. So now if I go by that, sine omega t plus pi by t is the same thing as saying y equals to a cos of omega t. So this particular thing, you can see it by my back. If you can see my back very well, you can see a cos of omega t is what? The way we represent this formula, I'm going to highlight for you to see it very clearly. This particular formula here, like yesterday, is the equation we use for a body that is not starting from what? From initial position. So when a body is exhibiting simple harmonic motion and it is not starting from the initial position, this is the equation we use. So keep this at the back of your mind. So it is very, very important. I hope you understand that, whereas this is the general equation. So what I've done is I've just applied my trigonometric value, which is also one of those things you need to keep the back of your mind. Now that we have the general equation, this is general equation. General equation I write as GE. Now we can now study the velocity and acceleration of SHM in details. Now that we have the general equation, so that we can keep all those formulas that is needed at the back of our mind. So let's quickly study that. Or before I go to this point, now that you know this, let's keep these two formulas at the back of your mind. This is just what I want to explain here. This is for body that is not starting at what? At the initial position. As pi by 2 is the same thing as what? Cos. Do you understand what I've done here? I've only changed pi by 2 to cos, and that is what I have done. So keep that in mind. This is the general equation, and this is for body that is not starting from what? From rest. So we move to the next point. So the next point says we want to discuss about the velocity and acceleration. It's not up to 15 minutes. Why am I saying signal? So the velocity and acceleration of SHM. Now about velocity and acceleration. Velocity, we have just discussed that we have the general equation. I hope students can quickly remind me about the general equation. I gave y is equals to a sine of omega t plus what? Plus alpha. Put this a bit, alpha, which is the general equation. Please keep that in mind. This is the general equation. So now we need the velocity from this. We know when we take velocity as a function of what velocity is given by formula, the change in displacement, a bit the y by dt. I hope students are still here. So if we do that, what am I going to have? I'm going to have I'm only differentiating this, every other parameter remain constant. So the y by dt, which is velocity, is now going to be y by dt, which is velocity, will now be equals to, I will take a is constant, it's not changing. I differentiate omega t. What am I going to have? Omega. So you have a omega. Sine is going to give me what? Cos of omega t plus alpha. I hope students understand this. What I've only done here is what I have only what differentiated. I did not do anything that is what magnificent. I did not do anything that is magnificent. So directly, if you see this now, I will now write this in another way. You need to understand some stuffs. I have done videos on this before on my previous channel, which most people are saying they want to understand how I come about my derivation. I'm not going to rush you here. From your trigonometry, I need to just show you some things. It is not always needed. You know, sine square theta plus cos square theta is equals to 1. I hope students still remember this basic law, because it's very important for you to know this. Because if you don't know this, it will cause a lot of what? A lot of havoc. So now, sine square theta plus cos square theta is equals to 1. So if I make cos square theta, sorry, a formula, what will I have? I'm not supposed to be showing this, but because of time, they will soon ask me to leave, is equals to 1 minus sine square theta. Why am I doing that, my dear student? Because I have cos here. So I want to make cos theta as a formula. So if I make cos theta as a formula, what do you know? You what? Square root of what? 1 minus, I hope students are here, minus sine square theta. Basically, that is it. So the same thing I want to do here, so that I can write velocity as a function of time, is very, very important. So if I do that, I'm going to have V is equals to, please follow me up, A omega. What is cos theta now? You know, now my theta is now cos of omega t plus what? Plus alpha. I will now take it as what? Square root of what? Talk 1 minus, very good. 1 minus, what is 1 minus sine? It will be your sine square. What's my theta now? My theta is omega t plus alpha. Sine square omega t plus alpha. So this is this. I'm trying to write this particular equation you see here, my dear student, is very important. You keep it in mind. Let me highlight it. Time is always the major factor. Now, this formula you see here is used to calculate the velocity of a body undergoing simple harmonic motion when it is given as a function of time. When it is given velocity, when it is given as a function of time. What do I mean by velocity as a function of time? If an examiner is giving you question, and the question that the examiner is giving to you is related with respect to time, like he's writing an equation, and the equation is with time function. That means you can see that time is here. Calculate the velocity of a body that has a time of this one, that start from a what initial phase of 5. This is pi by 2. Have an angular velocity. You understand? This is the equation you are going to use. Now, velocity can also be written in the second formula as a function of displacement, which is what most of you actually know very well. So let's write it as a function of displacement. Now, if we write velocity as a function of displacement, you and I know that it is simple for us to get that as you know that we know that y is equals to what? From what we've studied, y is equals to a sine of omega t. So if I make sine of omega t sort of formula, what will be the answer? Sine of omega t, I just want to show you, is equals to y over a. So that is what I want to do here, my dear students. So now I have sine square of omega t plus alpha. So it will be y over a all squared. So velocity as a function of displacement will now be equals to, are you guys following? To be v is equals to, we have a omega. Now I have, what I have here is square root of 1 minus sine of this one. You can see I've turned to y over a, 1 minus y over a, all what? All squared, because this is having square. So I'm just trying to show you step by step. So now if we substitute, if we expand this one, at the end of the day, we are going to have V is equals to, directly, this will give us omega. You take a root of, expand all this. If you have time, you can do it. The famous formula, you have a squared minus y squared. So this is the formula, the second formula of velocity as a function of what? Displacement. So I will also highlight that in another color for us to understand well. I need to excuse you if you have any question. So now what I'm trying to say here is that velocity as a function of displacement is given as what? Omega. You open the what? The root under the root of a squared minus y squared. What does a stand for? The amplitude. What does y stand for? The displacement. So we need to understand, because we are talking about SHM, my dear student, there are different cases of undulation. Now, we've talked about some points before, but now maybe we should quickly refer back to what we have studied for understanding's sake. We say this is the mean position. These are the extreme positions. Now, at the mean positions, listen now, velocity is a maximum at mean position. You can keep down a note. At extreme position, velocity is what? Velocity is what? Minimum. Why is it so? When body is here, maybe I should quickly recap from what you have learned in junior classes. You know, we are talking about undulation of to and fro, which we call simple harmonic motion, in which acceleration is always proportional to its displacement from that position. So now, a quick point about what I'm talking about is that if acceleration is equals to what? Is proportional to displacement, which we've talked about for SHM every time, at this position, velocity is minimum. So we know at this particular point here, acceleration, because as you are moving from here to here, what happens? The body is increasing in distance, right? So it is accelerating. So acceleration will be maximum here. Please, these are things most of you see in OBJs and you miss in multiple choice question. You just need to be careful. Exam is not that tough. So now, when body is at this position, we call acceleration is what? Is minimum. You can see velocity is maximum at mean position. Acceleration is minimum because the body is not accelerating at mean position. Another important point I can quickly write is what? At this point, you say potential energy is what? Potential energy is zero. It's minimum. Minimum means it's zero. Then, yeah, what happened? Kinetic energy here is what? Is zero. It's minimum here. But you can say potential energy is what will be maximum, right? At this point, because it has moved. We've talked about work energy and power. You can watch our video on that. You know, any class you say energy is what? Due to rest. That's the way you define. I don't define my own potential energy like that because there are limitations to that definition. But that is not what I'm doing here. So what I'm saying, my dear student, is that be careful about all these things. At this particular point, kinetic energy is maximum. So all these are basic things from early classes. You can keep down a note for you to understand basically what is needed to pass your examination. So velocity as a function of displacement, velocity as a function of time, both formulas are very important for dear students to keep in mind. The next one is, this is a little bit rough, but there's a reason for it being rough. And this is acceleration. So we continue from where we stopped. And we go to acceleration. So about acceleration, we can take that. Acceleration is the rate of change of velocity vector. And we take it from here. Velocity from here is given as, you can just follow a omega cos of omega t plus alpha. Alpha, which means our initial phase of what motion. Now, our initial phase of simple harmonic motion. So from here, we know the v by dt is acceleration. When you differentiate acceleration, velocity with respect to time, you are going to have acceleration. We've learned about it. So let's differentiate this thing. You know, I told you everything is a constant except what? Omega t. When I differentiate omega t, I'm going to have omega. So that omega is what we multiply this omega. So I will say acceleration is now equals to a omega times the omega of here will give me a omega square. So I'm repeating every function. Sine, cos will give me minus sine. I hope you have minus here. You know, sine minus sine. I've put the minus outside, as you can see. Then I repeat what I have in the bracket, omega t plus alpha. So if you remember from the first thing we've done, from here, I will take it for you to see it. What is a sine omega t plus alpha? What's that, guys? A sine omega t plus alpha is what? Y. So I'm going to substitute A sine omega t plus alpha. I will get what I have gotten in the last word. When we talk about representation, I will have A is equals to, what about this, my dear student? This formula here is very important too. Please keep it in mind. This one is giving acceleration as a function of what? Time. So acceleration as a function of time, that is the formula you use. Then if you substitute y is equals to A sine omega t. Please, let's do this together, dear student. A sine omega t plus alpha is y. So I'm going to have minus A, then we have a minus, where is A has gone? I'm substituting A sine omega t plus alpha to be what? Y. A sine omega t plus alpha to be, I have minus omega square y. So this is another formula which you have learned the other time for acceleration as a function of what? As a function of displacement. So keep that in mind. And the major point about this formula is just, most of us find solace, enjoy cramming formulas and use it to solve questions. But there might be some questions that are not coming directly. That is why to know concept is very important too. Some exam require you to know how to derive, and that is why we are doing all this. So my point, I'm sorry for rushing. I have other videos on this too, in which I take it slow and steady for those of you, but you can as well download the video and watch it again and again. If you watch it again and again, you are going to get all what I've been saying with respect to this. So now, from my point, so far so good. I'll just clean up this side. For understanding sake, then we bring out different formulas for acceleration, and I think that is where I will stop. I still have energy stored. I know there should be energy stored in the slide. I'm very sure about that. Now, from the formula we have now, if we say at mean position, velocity is maximum. If at mean position velocity is maximum, you know this with what is 0. So if this is 0, x is 0 at mean position, velocity is maximum at mean position. So that means it has displaced what? Y equals to 0. So the formula we use is what? V is equals to A what? Omega squared. You say A omega. I don't know if you understand. V equals to A omega. So keep this in mind, is important, which is what you know from what you studied before under circular motion. V is equals to R omega. We don't use R here, we use it. How did I come about A omega? If it has displayed the distance of what? 0. 0 square is 0. What's this? You have A square. When you square this one, you know what you're going to have. I don't have to waste your time. Wherever at extreme position, the value of velocity is what? Value of velocity at extreme position is always going to give you 0. I've explained that. Maybe we should not try that. So the last point I want to talk about, the same thing to acceleration. This is acceleration. You know, at maximum position, the body is what? Accelerating. But at mean position, acceleration will be equal to what? 0. So we don't need to write. At mean position, velocity is not 0. It is maximum. So note that. So the next thing is just for us to add another important point we call differential equation of our SHM. You can be asked, A-level students in particular. Differential equation, or you say general differential equation of SHM. So it's just a quick thing you can just see. How do we come about differential equation of SHM? When we differentiate this thing twice, we are going to have the what? Acceleration. So now look at this. You can say, if I differentiate y twice, if I differentiate y with respect to time, I'm going to have velocity. If I differentiate velocity with respect to time again, I'm going to have what? Acceleration. So now my point is that differentiating the square y over the t square, I hope students understand differentiating twice. So you say y prime time, anyhow you want to write it, y the t square, then is equals to the acceleration. What is acceleration? Negative omega square y. So if you now collect like times, you have a d square y over the t square plus omega square y is equals to 0. This equation you keep down in note is called general differential equation of SHM, which we use in advanced physics to solve a lot of questions. So this is called general equation, general differential equation of SH. So keep it in mind. It's very important. Whenever I mark a formula, I told you, for those that are just joining my class, you have to keep it in your short notes. It's important. Even though we might not be solving numerical related to them for now, I told you, after we are through with all concepts, numerical chapter-wise, tough questions, you call them, will be taken and we are going to be solving one by one. So we move to the last part, which I will not waste up to 2 minutes on that. And that is energy stored by particles in simple harmonic motion. Hey, time up. Okay. This is not time up, please. So energy stored by particle. We've talked about energy and we talk about energy. The two types of energy that will be stored in body that is going to and fro will be what? Potential energy. We can say total energy. You know, by now you should get used to physics concept. You know, anybody, when I say anybody, I don't mean anybody. I'm talking any system of bodies. You understand? That is what? Gaining energy, we also lose energy. And there are two forms of energy. I told you, potential and kinetic. The other type of energy in work energy and power is called dissipated what? Energy. So we have two energy which is stored, is potential energy and what? Kinetic energy. If you want to analyze, because I don't want to waste time because of time, you can always see that potential energy at any point in time will be what? Will be zero. And the kinetic energy will be what? Half mv squared. Now, if you consider extreme position and mean position, it will always be potential energy will always be what? Zero. Because it's always keeping the body at what? At rest. So the total energy in a body undergoing or system of what? Body or system of particles undergoing SHM will be equals to 0 plus kinetic energy is what? Half mv squared. So from what we have learned, my dear students, what is the formula for velocity of simple harmonic motion? Do you remember that, you know, velocity we say is equals to a omega at a particular point. So if you say total energy is equals to half, you know, 0 plus anything is still that thing, half m, what is v? A square omega square. Somebody is saying alpha. Alpha is because I have only substitute v to be equals to a omega. So a omega all square will give me a square omega square. This formula I have marked again should be written down in your formula notes. Do you understand? Sorry guys for rushing you. This is just basically what I believe you have studied in your classes. So again, we can also write it as a function of time. Remember velocity as a function of time, and as a velocity formula is a omega cos of what? Omega t plus alpha, right? Omega t plus alpha. So if you write down when you say total energy can also be in form of, I'm not going to waste your time, half m, I have a v squared now. I'm having a, you can see a omega cos of, don't be scared, omega t plus alpha, all what? I close the big bracket, all is squared. Can you see this? Can you see this now? I believe you can see this. This is v squared. V squared, I'm substituting this value here. So this is another important formula you keep in your formula book. Depends on the nature of the question. This will depend on what you are going to use to get the answer. So guys, it's very, very good to understand physics in different ways. And you can also talk about average energy. Another important thing is average energy. I'm being given time to stop this class. Average energy, average energy, average energy. But I won't stop this class until I do the illustration that is prepared by the student here. So average energy is always equals to what? Half of the initial energy. That is what you just need to know. Half of the initial energy. So half of the initial energy, I can do that. There's what they call sinusoidal graph, my dear student. The square of sinusoidal function is always, some students are saying, what is sinusoidal graph? What is sinusoidal? A sinusoidal, some people are not math students, I understand, I concur. And it's a type of function that is moving in this manner. You can see, you understand, like a sine wave. Math student can tell us more about that because I know they've done that before in their math section. You can see. So when something is like this, we say, when something has moved like this, sinusoidal, sorry, diagram not going to say, I am rushing. When something is moving like this, what you need to keep at the back of your mind is what? You say it has complete what? A circle. And a circle is equals to what? A revolution, 360, you call 2 pi. Remember, you say from early classes we've done about that, t equals to 2 pi over what? Over omega. This is a popular formula, which you say frequency will now be omega over 2 pi because it's inversely proportional to the period. Remember that we've also talked about all these shorty concepts, I call it. Now under circular motion. Now my point is, for every square of what? A sinusoidal graph, either cosine, either whatever, you are going to have, when you square it, it's always going to be what? Half, 1 over 2, half. What I'm trying to say here is that cos omega t plus alpha square here is going to give me 1 over 2. As a function of time, it's going to give me half of the oscillation. That is what I mean by that. So everything here is going to give me half. So if I multiply half by half, what is that? It's going to give me what? 1 over 4. So we say average energy is always 1 over 2. I'll just help you write it out because of what? The total energy. You can write it in this form. What's the total energy? Is 1 over 2 times m alpha amplitude square and omega square. What does m stands for? Because I don't want you to lose the root. Is what? A stands for what? M stands for what? Mass. A stands for what? Amplitude. Omega stands for what? Angular velocity. So please, guys, this is where we are going to stop here. But before that, remember, we also need to understand all these are basic things under a simple pendulum experiment, which is a very good experiment to illustrate our simple pendulum. I've talked about it under the aspect of circular motion. We derive the formula, but for those that did not join us there, we say when the body is tied up a ceiling like this, then let's change that color. That color is not that fine. Then we're talking about the length of the string as it is here. Then we say if this thing is released from that particular point, L, and it is moving to another point, it will displace an angle of oscillation. You and I know very well, we've talked about this. The body is released here from that point. Sorry, I'm rushing because of time. And it comes here. God. Waiting for this to come up. Okay, fine. So as you release it from that point, it will come like this. Then it will have something like what I'm trying to picture. So it was dropped at this point. Then it will move like this. Diagram not going to stay. It's going to have the displacement of theta at this particular point. This is the initial height. This is the new height. It has moved up a height of h at a particular period t. You remember that? So we say we can set equilibrium because the body will come back to this initial position. Is going up to and fro. You understand? So for every to and fro, we said capital T is 2 pi by omega. Remember that. So there are some things we need to understand from this simple pendulum experiment, that the period of motion is proportional to the square root of the square root of the length. That is very, very important. And the period of motion is also proportional to, is inverse proportional to the inverse of a square root of the gravity. So this is two things that we conclude from simple pendulum experiment. I've talked about this using kinetic energy equation. You understand what I did for you. You know, the body, we have centripetal force here. We can just say tension is here. Remember, tension of the string. But this has been done under circular motion. You can balance whatever you want. That is T cos theta, T sin theta. Then weight is acting downward. T cos theta is balancing the weight. T sin theta is balancing the other force that is responsible for the motion here. So which is mv squared over half. You can always get any formula you want to get. And if you want to use kinetic energy, the body was dropped from there, goes to a height. So it is doing a negative work. A negative work. Potential energy will now be negative mgh. So here, the work done here, to move from here to this point is what? Half mv squared plus mg minus mgh must give you the final work done at this point to come back to initial position, which is what? Half mv squared. So initially, you can take this one to be u, final, this one is v. You come about formula. I have done all these under circular motion with you, so you can watch that. So my point here, which is most important point I want to bring out, is that from conclusion of simple pendulum experiment, we say the time period for this thing to go back and forth, which we call to and fro, is proportional to the length, and it's proportional to this. So this is a factor. If somebody asks you what are the factors that affect the period of what? Of a simple pendulum, the answers are the length, you can say, and the what? Acceleration due to what? Gravity. So these are the important things my student can remember. So we compute the two formula together. We say T equals to, for every oscillation, we say it is 2 pi. I told you that's 360 degrees. So we put the constant. The constant we use is now 2 pi. You understand? Whenever you change variation to a constant, there will be a constant. We have under root of L over G. This is a famous formula you can always keep also at the back of your mind. Because of time, that's why I'm rushing, my dear students. Sorry about that. I just have to finish up everything. And clear all concepts and all doubt from your mind. Now, about this one, we can also conclude that, okay, fine. Then from the experiment, it was concluded that what the mass of this spring is what is an ID spring. So if you are talking about an ID, it is only an ID spring that can follow this condition. If it is not an ID spring, it will not work. So we conclude from the experiment that what mass of the string, let's say the conclusion, mass of the string is inextensible. You know the meaning of inextensible? Cannot be what? Stretch above what? It's what? Elastic. So that's that about that. This is just a quick one, my dear students, quick bite, and I hope you understand it. And if not, watch the video over and over again, download it. I know you are going to get it. Let's quickly look at the illustration as prepared by the student, not to waste our time. I might not actually do all the questions because of time. Time is fast spent. We have the first one. We have the motion of a body in SHM. The motion of a body is simple harmonic if the dash. I told you condition for simple harmonic. Acceleration must always be proportional to what the displacement. That's the condition. Acceleration is always directed towards a fixed point. Fine. As a part of the motion is what? Straight line. You can see these are conditions, but they are not the major conditions. No definition is acceleration is directed towards fixed point, but it's proportional to what? Displacement. Acceleration is directed towards a fixed point and proportional to its displaced distance, which is absolutely correct. This is the question answer because it goes with what we have studied. Next one says a particle exhibiting SHM has a frequency of this and an amplitude of this. Calculate its maximum frequency. What is maximum frequency? We have studied maximum velocity. We say maximum velocity at mean position is given by, please you talk, a under root of omega square minus y square. This is the formula I gave to you if you are following. So now from here, we can just say we know A is 8 times 10 to the power negative 3. I presume that is what the student writes here. Then at mean position, what is y? Y is equals to 0 at mean position, starting from. So particle is exhibiting SHM, frequency is what? So I need to get to omega. What do I know from circular motion? Omega is equals to 2 pi f. I hope students can remember this. So we can say 2 pi f is 2 pi is 3.142. You understand that in terms of revolution, 2 times 3.142 times the frequency was 50. You can go by your calculator, 100, or you say 100 pi. I don't have time. I want to give answer in terms of pi. Maybe it will help us. So we can say V is equals to, what is A? A is 8 times 10 raised to the power minus 3. Square root of anything minus 0 will still be that in 100 pi. I hope students are here. What do? I square both sides. That is 8 squares are 64 times 10 raised to the power minus 3 squares are 10 raised to the power minus 6. Then square will remove square root and multiplying by 100 pi. 100 is 10 raised to the power 2. So V will be equals to 64 times, don't mind me, 10 raised to the power 2 minus 6. I'm using indices. That's 10 raised to the power negative 4 pi. Very good. Students are here. This is very good. We have a 64 times 10 to the power of negative 4. It's going to give you, you know what to do that, 0.0064, right? That is 0.064 pi meters per second. So that is the answer. And if the answer is not in terms of pi, what do? You multiply by 22 over 7 or 3.14. So I'm rushing, but that doesn't make me not sure how to solve your question. The next one says a simple pendulum is having this period. A simple pendulum 0.6 meter long has a period of 1.5 seconds. What is the period of a similar pendulum over 0.4 meter long in the same location? So if it is in the same location, this is going to give us we say period of the simple pendulum is proportional to the square root of length. So the first length is given as 0.6 meter. The period was given at that particular length was given to be 1.5 seconds. So we are looking for the mean period, that is the T2. I'll call that X. when the similar period has a length 2 over 0.4 meters. So since this is proportional to this, if I'm setting the relationship, it should be saying period 1 divided by period 2 is equals to length 1 divided by length 2. For those who are saying, how did I come about that? This is t equals to k root l. Make a sort of formula, you have a t over root l. When they are more than 1, you have t1, l1, you have t2 root l2. So this is the way I come about that. So if I say t1 l2, then it's the same. This expression is simple as this. So this will be very easy, simple for me to plug in parameters and get the answer. So you can do that. T1 here is 1.5. I'm looking for this one. This is x is equals to square root of first length is 6, 0.6 divided by the second length is so I can just say, how do I do this? What do I know? I square both sides. And if I don't want to square both sides, I can write this one as a 6 over 4. If I write 6 over 4, 2 here, 3, 2 here, 2. That's just another way to do it. I'm just using my own brain like that, which I believe you can do better. 1.5 over x is now equals to, we are squaring this one, is equals to 3 over 2. So directly, I have x squared. This is equals to, I just want to do it directly, 1.5 squared times 2. I'm dividing the answer by, and what I have here, that is by 3. So if I go by that, s will now be equals to square root of, if I take square root of this one, I'll still get 1.5 back. 1.5, and I have a square root of 2 over 3, which is the way examiner will leave the option. Me, I'm sure about that. And that's why I'm doing it in this way. So that's what we calculated is in seconds, because we are talking about time. So be careful about, because this is question that calculator is not required. I've only used my knowledge of mathematics to concrete. So about the last question for this slide, the last question is the question is asking us a simple pendulum of mass m moves along the arc of a circle of radius r. Then in the vertical plane, as shown in the figure, what is the work done by gravity in the downward swing through the angle theta to 0? So if the body is going downward, it's coming downward, what we have been to here, the work done by downward swing. I've done this one under what happened. So if we go by that, we don't need to waste our time. For vertical oscillation, talking about work done, theta will come here. This is theta. You can see the body is starting from here. I'm not going to waste time because we already know where we are going. It's having a radius of r, fine. So we have to resolve. The body now come here. It has covered a particular height from here to here, which you can just do like this. For those of you, if you like, this should be a straight right angle triangle, not drawn well, but you shall visualize this one like that. So this is a triangle. It has covered a particular height. This is the height. This must be like this so that this will be straight. So diagram is not drawn to scale, it's not drawn to scale. So this has moved from this point to point. So if the height here was h, they said, what is the work done? Like I said, if the total length from here to here is the length, so here to here is the length. So here will be L minus what? H. You understand what I mean by that? Because the body is, so if work done is done by that, this is theta. Theta will turn it here. Weight is equals to the mg is acting in this downward direction. You know what I mean by that? You can resolve two components as you already studied, t sine theta and t cos theta. As you can see, tension here, this is opposite. I'm taking this one now. This is what they call radius. So if you are going by that, this should be the tension and that should be the radius. So what I'm trying to say now, if we resolve that, we are going to have r sine theta. You can see horizontal component is sine theta. Vertical component is what? Cos theta. So following what you have there. So r cos theta for equilibrium, we balance that one. And if r cos theta is equals to mg, but what I need to know about the length here is that at this particular point, if I say R cos theta. You know, work done equals to force times the displacement. So which is what I'm trying to do. So force is mg, which you all know because we are talking about weight in downward direction. The distance over here, we have to just resolve this one to component. Like I said, this is L cos theta, L sin theta. As you can see, this is R sin theta. We are considering this to be a right angle triangle. And this is what? This is R cos R cos theta. So if I go by that directly, L minus H equals to R cos theta. So you can say this is the same thing as saying H will now be equals to, at that particular H will equals to 1 minus cos theta. Like I said, L minus H. And the L of this thing is also taken to be R. So this should be like saying R minus H, because they take this length to be equals to what the length from there. So if R minus H equals to R cos theta, so R will be equals to, you can see you factorize 1 minus cos theta. Anyhow you want to do it. So what we are getting here is what? Mg. You know, everybody know force is what? Mg in direction of, and the distance covered there is 1 minus cos theta, because we are having that one to be H minus H cos theta. So H minus H cos theta will give us, what is that? H will be equals to what? Factorize H open bracket 1 minus cos theta. So that's what I did, guys, for you to understand what I mean. So this is the right answer. And again, if you don't want to disturb yourself, I have derived this equation formula in our previous work. So guys, this is where I'm going to stop, and we can actually watch all these video series available on the Academy Physics channel YouTube. So don't forget to subscribe, like, and share the page. See you soon. Do have a wonderful day. Bye.